Hello everyone. I Purvesh Nanavati welcome you to my YouTube channel Welding Education. Well, in this video episode, I will try to explain you the application of WRC 1992 diagram for predicting the weld metal composition using a case study of dissimilar metal joints between carbon steel and stainless steel material using a matching filler metal and at various dilution levels. The analysis of weld metal composition on the predictive diagram, WRC 1992 diagram. As you know, the WRC 1992 diagram is the latest one and it is used for predicting the weld metal composition at different dilution levels for austenitic and ferritic austenitic duplex stainless steel material. So let us now discuss a case study. Well, the inquirer asked about a question. The fabricator has joined between low carbon steel ASI 1018 steel with ASTM A240 type 316L using a AWSA 5.9 specification 309L filler metal, and the test certificate is provided by the inquirer, which is shown in the table. Now, when you look at the composition of ER309L test certificate provided by the inquirer, you would see a level of nitrogen in weight percentage around 0.132, and the carbon, manganese, chromium, nickel, molybdenum, niobium, copper. These elements are applicable for our chromium and nickel are only tabulated here, rest are ignored. So the problem statement is that the fabricator welded AISI 1018 carbon steel with SS316L stainless steel using a ER309L filler metal, but he found when he checked the composition with a PMI method, he found the composition somewhere around of 308 material. So the fabricator is observed to be using a right kind of filler metal, that is ER309L, for GTAW process to join to these two metals, AISI 1018 steel and type 316 stainless steel. So when the filler metal composition is double checked with the specification of SFA 5.9 covered under ASME section 2 part C, all elements were found to be in the specification range except nitrogen, which did not match with the 5.9 m specification standard. The difference in nitrogen concentration in purchased consumables might be easily detected. So these in above tabulation, you can see the encircled, red encircled uh, uh, figure 0.132 weight percentage nitrogen was detected in the TC of the fabricator, and this TC is showing a nitrogen which should not be a part of this chemistry, and it has to do with the hot cracking susceptibility of the weld metal. So for reference, the chemical composition of the ER309L covered under SFA 5.9 specification is mentioned in this table as per ASME section 2 part C, specification for welding rods, electrodes and filler metal. You can see these this specification does not specify nitrogen content in the filler metal composition. There is no mention about the nitrogen content. Rest are there: carbon, chromium, nickel, molybdenum, manganese, silicon, phosphorus, sulfur, nitrogen dash, and copper. So we need to understand the effect of this uninvited nitrogen content that comes through a filler metal composition on the dissimilar joints between carbon steel and stainless steel weld metal ferrite content. Because weld metal ferrite content and final mode of solidification and solidification tendency, this analysis can be done by WRC 1992 diagram. Before we carry out the analysis using the actual consumable use as mentioned in the TC, first we will try to understand the what is called as safe weld metal composition, and that does not contain any risk of hot cracking. So let us employ the standard ER309L consumable composition as provided in this table 2. So using this composition, we'll try to plot the composition on the WRC 1992 diagram, and so when the composition of the chromium equivalent, nickel equivalent, I hope you understand the chromium equivalent, nickel equivalent. So chromium equivalents are chromium itself, molybdenum and niobium, and nickel equivalents are nickel, carbon, nitrogen and copper. As you can see in the y axis, there's a nickel equivalent is mentioned, and on the x axis chromium equivalent is mentioned. So the chromium equivalents alloying elements are those elements which tends to uh, stabilize the ferrite, and the nickel equivalents are those alloying elements which tend to promote or rather stabilize austenite phase. So this nickel chromium iron and sometimes molybdenum alloy will try to put the chromium equivalent and nickel equivalent value of the C1018 carbon steel with SS316L composition and the standard ER309 welding consumable filler metal. Now considering some portion of dilution, so this is a case 1. So case 1 is considering a dilution of 30 percentage of filler metal dilution. So you can assume that when we make joint between uh, ASI 1018 steel and carbon steel and stainless steel 316L, so we can consider 15 percentage dilutions, 15 percentage dilution from each base metals, and the uh, chromium equivalent and equivalent of these of all base metals, two base metal 1, base metal 2, and the welding filler metals are plotted on this WRC 1982 diagram. And when we uh, consider 30 percentage, say from this point to 30 percentage, we can come to a weld metal composition. Now these two base metals, when we plot these two base metals, we need to connect this 309L to the midpoint, because uh, we assume that the 50-50 percentage of from each base metal. So here you can look at the short axis view for better visibility of the weld metal composition in this figure. So considering a 30 percentage dilution, so when we take a 1/3 of these red line, we can come to a weld metal composition. So you can check this weld metal composition is somewhere after this green dashed line, and you can see this AF, FA and F. These are the solidification modes, and this dashed thick line blue, it is a solidification mode boundary between A and AF mode. A means in fully austenitic mode, AF mode is primary austenite and secondary ferrite. Then FA mode is primary ferrite and secondary austenite, and F mode it is in fully ferrite microstructure. So the austenitic stainless steel most of the time solidify in this mode A, F, and Fa. So preferably it should solidify under Fa mode to prevent hot cracking issues. And this duplex ferritic austenitic weld metal solidify in fully ferritic structure. Again, the fabricator is using a GTAW process, which is a manual process, we know. So the dilution of the base metal to the filler metal composition may be varying from 15% to 20%. So now considering a worst scenario like total 40% dilution of the ER309 and filler metal. So for 40% dilution, we may consider 20 percentage from each base metal, 20 percentage. So under this condition, we may still obtain 1.5 to 2 Ferrite number and AF mode of solidification, which we can see in this line. You can see the when this line WM weld metal composition is just you can see here 0, 2, 4, 6, 8, 10. These are ferrite numbers. So we can see this 1.6 to 2 percentage ferrite number we can easily get with a 40% dilution of the filler metal. But to avoid any risk of hot cracking in weld, the better practice is to keep the low heat input as much as possible. And there is also a better practice, a good practice when we are joining two dissimilar metals, that welding arc is to be or arc heat must be fall on the SS316L base metal side and less on the carbon steel side, so that these will reduce the dilution of the carbon from the carbon steel material into the weld metal, and overall reduce the diamonds dilution of the alloying elements into the filler metal composition and weld metal uh, deposition. So in this case, considering a 10% dilution from the carbon steel into the filler metal composition, rest 20% from the SS316L into the filler metal. Now we can comfortably get around 5 to 6 ferrite number and Fa mode of solidification, and which is without any risk of hot cracking of the weld metal. And this respective weld metal composition on WRC-1992 diagram is shown in the short axis graph as a case 3. You can see this, the point what we get here, it has a uh, ferrite number around 5 to 6, because you can see this here 0, 2, 4, 5. So it is between the 5 to 6. And secondly, the mode of solidification will be AF. Sorry, nearly FA mode of solidification. So this is a case 3, considering a 20% dilution from the SS316L into the ER309L filler metal composition. Now let us turn back to our main point of discussion, because the above all three cases were above all three case 1, case 2, case 3, they as well considered using a standard filler metal chemistry that is commercially available for ER309L for welding two dissimilar metals between carbon steel and stainless steel. Now we want to figure out what will happen to weld metal composition when there will be a presence of nitrogen in the weld metal chemistry. So let us now focus on the, or let us use the uh, composition of the that is provided by the inquirer, the test certificate of ER309L, which was used by the fabricator. You may see here carbon is 0.08 weight percentage, manganese 1.82 weight percentage, chromium is 23.6 weight percentage, nickel is 12.70 weight percentage, molybdenum is 0.04 weight percentage, niobium is absent, copper is 0.06, and nitrogen is 0.132 weight percentage, which is very much undesirable with respect to weld metal composition that we are going to see again in our next analysis. So by plotting the composition of the base metal and filler metal composition as per the supplier T sheet that is given in the table 1, The respective position of the weld metal compositions can be shown in this figure 5. So you can see this is figure 5 is a special case. It's a kind of analysis showing that as low as 0.132 weight percentage of nitrogen, and even with low heat input and with only 30% dilution, 15 percentage from the each base metal contribution. So this filler metal, the weld metal chemistry can be pushed towards A mode, austenitic mode solidification with very fewer traces of ferrite. So here you can see the red arrow. The weld metal composition is almost with the A mode of solidification, purely austenitic mode of solidification, and with a very least traces of ferrite, right? The ferrite will be less than 1.2 or somewhere 1. So this situation will compel the weld metal composition to undergo a solidification in fully austenitic mode and or austenite and some little or no ferrite. So this ferrite-free composition is highly undesirable composition and threatening to the life of the weld metal. So using this short axis graph, we can see the position of the weld metal composition. The role of ferrite or the content ferrite is very much important with respect to the dissimilar metal joints in stainless steel, because when we are joining stainless steel with stainless steel with a matching consumable, say for SS304 we use ERE 308, or for joining the same base metal SS316L with EER 316L filler metal, there is no question, because the chemistry of the filler metal is such designed that we can comfortably get the ferrite number between 5 to 8. But when we are joining carbon steel with stainless steel, we always have to look into the deposited weld metal chemistry and different dilutions level. We have to maintain the heat input as low as possible, because somewhere if we can get the ferrite number less than the 3 or less than 3, the primary solidification mode will not be ferrite, or rather there will not be traces of any ferrite, and solidification mode, primary solidification mode will be the austenite only. So this, why this small ferrite content is very much important with respect to the weld metal, because the presence of ferrite in a weld metal can absorb the low melting point elements like sulfur and phosphorus that may be accidentally present in the weld metal. So this ferrite is a sink for those low melting points elements, and this, because this low presence of these low pointing elements can wet the grain boundary, the solidified wet boundary, and they can segregate, because they are the last freezing elements. They can segregate at the weld metal composition, and under the cooling stresses, these grain boundaries are separated, the grains are separated. We define them as a crack, as a solidification crack. So, and there are many proposed theories, but the one of the satisfactory, one of the promising theory is the solubility limit of this ferrite content with respect to the melting low melting allowing elements, and secondly the grain boundary form, because the when the weld metal composition is solidified in only primary solidification, austenite grain boundaries are very easy for the crack to propagate through, but this austenite ferrite boundary is a zigzag boundary. So when we have some traces of ferrite, these AF boundaries can not uh, can prevent the crack to pass through, and the crack cannot be easily through this ferrite and austenite zigzag boundary. So now you can understand the presence of nitrogen, because nitrogen is a strong austenite stabilizer. So weld metal ferrite number reduces dramatically with a very minute amount of nitrogen dilution from the weld metal into the filler metal, and To add in that, carbon is also a strong austenite stabilizer. You can see on the y-axis nickel equivalents. Uh, Carbon is given a coefficient of 35, as well as nitrogen is given a coefficient of 20. So they have a huge role to play in the uh, stabilizing the austenite phase. So this carbon and nitrogen, they have a perhaps they have a combined effect that the weld metal composition is landed into a very unsafe condition and is prone to solidification cracking. So at the end of this video episode, my recommendation is to use a uh, proper uh, uh, filler metal and to check the chemistry of the filler metal either with the EQT or by the supplier's test certificates with the um, uh, ASME section 2 part C consumable uh, certification, and using a low heat input as much as possible. And when we are joining two dissimilar metals, directing the arc energy towards the stainless steel sides rather than carbon steel sides, so we can prevent the dilution of carbon into the weld metal composition, and we can minimize any risk of you know reduction in the ferrite number and ferrite content. So we can avoid the risk of solidification cracking. Another recommendation is, besides using the PMI instruments, I would rather advise to use a Fisher-Mac ferritoscope instruments that's calibrated with AWSA 4.2 to better check the weld metal composition experimentally. And secondly, the application of weldment if is in corrosive environment. So it is better to use ER309L MO filler vial containing 2 to 3 weight percentage of molybdenum that can take care of the pitting corrosion resistance in service than to use a ER309L filler metal only. So I hope you found this case study very interesting, and this case study is already available on my technical blog. You can uh, read this interesting case study on my rather many case studies like this on my technical blog www.weldingknowledge.co.in. So for now, uh, we'll see in our next class. So thank you very much. And if you like, you can subscribe to my YouTube channel, Welding Education, or you may subscribe to my welding technical blog, weldingknowledge.co.in, and you may provide any technical problem. And thank you very much for your patience listening. Thank you.